We've all heard the stories, a jet breaking the sound barrier, a sonic boom echoing across the sky. But what happens when you go much faster? Not Mach 1, but Mach 5 and beyond, the hypersonic barrier. At these speeds, the air doesn't just compress, it transforms, behaving in ways that defy common sense. The very materials of the aircraft are pushed to their limits, and the air can become a glowing, electrically charged plasma. Today, we'll explore what really happens when a vehicle enters the hypersonic regime. 6 critical effects that challenge engineers and physicists. From air catching fire to vehicles vanishing from communication, it's a journey to the edge of aerospace engineering. And it all starts with a whole lot of heat. The first and most relentless problem at hypersonic speeds is heat. Colossal, destructive heat that pushes the limits of physics and engineering. At Mach 5 and beyond, air molecules slam into the vehicle so violently that temperatures soar past the melting point of steel, threatening to turn the entire craft into molten metal within seconds. The space shuttle's iconic black tiles were a sophisticated thermal shield, protecting it from being incinerated during the fiery descent back to Earth. These tiles could withstand temperatures hotter than lava, and their design was a marvel of material science. Today, modern hypersonic vehicles rely on even more exotic materials: carbon-carbon composites, ceramic matrices, and superalloys, engineered to survive where ordinary metals would simply vaporize. These materials are the unsung heroes, enduring the relentless assault of heat and pressure. But even these advanced materials need help. The heat is so intense that no single solution is enough. That's why some designs circulate fuel beneath the skin, absorbing heat and cooling the structure, a process called regenerative cooling. The fuel acts as a moving heat sink, carrying away energy before it can do damage. If the cooling system fails, the skin can weaken and rupture in seconds, leading to catastrophic failure. There's no margin for error at these speeds. Every part of the vehicle, its shape, the materials it's made from, and the cooling systems must work together in perfect harmony to survive the onslaught of hypersonic flight. Managing heat isn't just about survival, it's about turning a deadly enemy into an engineering advantage. The way heat flows over the surface can even be harnessed to improve performance, shaping the very aerodynamics of the vehicle. But this heat does more than threaten the structure. It fundamentally changes the air itself, creating a glowing envelope of energy around the vehicle. The next challenge is even stranger. What happens when the air is torn apart by the heat? At these temperatures, molecules split, and the atmosphere becomes something entirely new. The consequences are as strange as they are dangerous. Shockwaves, plasma, and unpredictable forces surround the craft, making control and communication a constant battle. Let's see what happens inside that fiery envelope, where the air is no longer just air but a turbulent, superheated sea of energy. The air itself is about to change state, transforming from a simple gas into a plasma, a new frontier for flight, and a new set of challenges for engineers to conquer. Breaking the sound barrier creates a shockwave, a sonic boom. At hypersonic speeds, shockwaves become a defining feature. The shockwave hugs the vehicle, forming a thin superheated shock layer where extreme physics unfold. Every control surface, every angle, spawns its own shockwave, creating a tangled web of pressure and heat. If two shockwaves intersect, they can burn through even the toughest materials. Some vehicles, like wave riders, are shaped to ride their own shockwaves, using them for lift and engine compression. But this makes them highly specialized, optimized for a narrow speed range. If the shockwave detaches, lift and control vanish in an instant. Mastering hypersonic flight means mastering these razor-thin, violent layers of compressed air. The shock layer is where the air's transformation begins. Inside it, things get even stranger. The air itself is about to become something entirely new. Let's step into the plasma bubble. The next effect is as spectacular as it is problematic. In the shock layer that forms ahead of a hypersonic vehicle, temperatures soar to truly extreme levels, so high that the very air itself begins to break down. Nitrogen and oxygen molecules, which normally make up the air we breathe, are torn apart by the intense heat. First, these molecules split into their individual atoms, but as the temperature climbs even higher, those atoms themselves lose electrons, becoming ions and releasing a flood of free electrons into the surrounding air. This process creates plasma, the mysterious fourth state of matter. Unlike solids, liquids, or gases, plasma is a glowing, electrically charged soup of ions and electrons. Around a hypersonic vehicle, this plasma forms a sheath, wrapping the craft in a shimmering otherworldly glow as it tears through the upper atmosphere at incredible speeds. But this plasma isn't just a spectacular light show, it acts as a powerful barrier, blocking and reflecting radio and radar signals. This means that, for a crucial period, all communication with the outside world is lost, a phenomenon known as a communications blackout. During dramatic re-entries, spacecraft like Apollo and the Space Shuttle would vanish from radio contact for several tense minutes, completely isolated by their own plasma bubble. Mission control could only wait and hope as the vehicle hurtled through the atmosphere, invisible to both radar and radio. For today's advanced hypersonic vehicles, this blackout isn't just a historical curiosity, it's a huge operational challenge. Pilots and ground controllers lose vital data and control, making these moments some of the most dangerous in flight. To overcome this, engineers are experimenting with new solutions. They're testing higher frequency radio signals that might slip through the plasma, and even injecting coolants into the shock layer to temporarily open up communication windows. In high-tech labs, teams are racing to find ways to keep the lines open, even in the heart of the plasma storm. The plasma doesn't just block signals, it can also induce powerful electrical currents on the vehicle's skin. This opens the door to futuristic control methods like using magnetic fields to steer or stabilize the craft, harnessing the plasma's energy in ways that were once pure science fiction. For now, the plasma sheath is both a shield, protecting the vehicle from some of the heat, and a barrier, defining the very limits of hypersonic flight and communication. But the challenges of hypersonic flight don't stop at heat and plasma. The environment is relentlessly hostile, and every second brings new threats. The structure of the vehicle itself is under constant assault, facing forces so intense they threaten to tear it apart at the seams. Every panel, every bolt, is pushed to its absolute limit. Next, let's dive deeper into the crushing forces at play. Forces that shape every aspect of hypersonic design and operation. Surviving hypersonic flight is a battle on every front. Heat, plasma, pressure, and speed all combine to create one of the most extreme environments imaginable. At these speeds, the air itself becomes a weapon, bombarding the vehicle's surface with unimaginable force and energy. The structure must fight to hold together, every component working in harmony to survive the relentless assault of hypersonic flight. At Mach 5, the air feels as dense as water, slamming the vehicle with crushing dynamic pressure. The structure must be both incredibly strong and impossibly light, hence the use of advanced composites. Violent airflow creates constant, high-frequency vibrations, enough to shake bolts loose and fatigue materials. Skin panels can flutter and tear themselves apart if not perfectly engineered. Thermal stress is another enemy. Different parts of the vehicle heat up unevenly, causing warping and internal strain. Engineers use expansion joints and special mounting to let the structure flex without breaking. Every force, pressure, vibration, heat interacts, making the design a complex puzzle. The margin for error is razor thin. Surviving these forces is a triumph of materials science and design. But even if the vehicle holds together, flying it is another challenge entirely. Let's see what it takes to control a hypersonic ride. Withstanding the heat and pressure is just the start. Surviving the brutal environment outside the cockpit is only half the challenge. Now you have to fly the thing, and that's where the real test begins. At hypersonic speeds, traditional control surfaces like ailerons and rudders become sluggish or even completely ineffective, trapped in the thin, superheated shock layer that forms around the jet. Here, even the tiniest change in angle can trigger massive, unpredictable shifts in lift and drag, sending the aircraft lurching in unexpected directions. To cope, many hypersonic vehicles are intentionally designed to be unstable, relying on ultra-fast computer systems to make thousands of micro-adjustments every second, far faster than any human could react. The flight control computer processes data from hundreds of sensors scattered throughout the vehicle, constantly translating this flood of information into precise, split-second movements. But at these speeds, moving a flap or a fin doesn't just steer the vehicle, it reshapes the shockwaves themselves, altering the entire flow field around the jet in ways that are hard to predict. The relationship between what the pilot or computer commands and how the jet actually responds is non-linear and incredibly complex. Sometimes a small input can have a huge effect, or none at all. To overcome these challenges, engineers are exploring reaction control thrusters, tiny rocket engines that can nudge the vehicle in any direction, completely independent of the chaotic airflow outside. These thrusters offer a new way to steer when traditional controls fail. Flying at these speeds is less like piloting an airplane and more like managing a controlled explosion. Every moment is a fight to keep the vehicle from tumbling out of control. The pilot, or more often the onboard computer, is constantly battling the laws of physics, making rapid corrections to keep the jet stable and on course. It's a relentless battle against physics, like walking a tightrope at 1,000 miles an hour, with no room for error and no second chances. And all the while, the vehicle may be flying blind. At these speeds, the windshield can fog or even become opaque, and sensors may struggle to keep up. Communication with the outside world can be cut off entirely, leaving the pilot and the jet isolated, unable to receive new instructions or updates. In these moments, all that remains is the sound of silence, the eerie calm at the edge of chaos, as the jet slices through the upper atmosphere, alone and untouchable. The plasma sheath blocks radio waves, causing a communications blackout, a critical operational barrier. The blackout is worst at high speeds and low altitudes when the plasma is densest. For minutes the vehicle is isolated, no data in or out, no guidance updates, no help from the ground. Military vehicles can't transmit intelligence, missiles can't receive mid-course corrections, crewed vehicles are on their own. Solutions include using higher frequency radio waves or shaping the vehicle to create plasma windows for antennas. The most futuristic idea, using magnetic fields to push plasma away from antennas, creating a channel for communication. But for now, the blackout remains a defining challenge. Every mission must be planned around these silent periods. Hypersonic flight is as much about surviving isolation as surviving speed. The sound of silence is the price of extreme velocity, and it's just one of many barriers at the edge of possibility. So what does it all add up to? Breaking the hypersonic barrier unleashes a cascade of extreme physics, heat, shock waves, plasma, crushing forces, instability, and blackout. Each challenge is linked to the next, creating a chain reaction of engineering problems. Hypersonic flight pushes the limits of materials, design, and control. It's not just about building a fast aircraft, it's about surviving an environment of your own making. These 6 effects define the next great leap in aviation. Which one surprised you most? Let us know in the comments. Thanks for watching. Subscribe for more journeys to the edge of science and engineering.